All right, everybody's favorite, periodic trends. Woo, love it. So, starting with atomic radius. So, we're going to talk about how the electron configuration can make you kind of compare certain properties of elements to each other, starting with how big they are. So, the distance from the nucleus to the valence shell of electrons. The general trend is you'll see that they increase in size as you go to the left, and they increase in size as you go down the periodic table. Why? Why do we increase in size as we go down the periodic table? It kind of makes sense if you look at the Bohr model. So lithium, for example, has 2 energy levels, but francium has 1, 2, 3, 4, 5, 6, 7. Okay, so obviously increasing the number of energy levels is going to make your atom a lot bigger. Not only because you're adding energy levels, but the more electrons you add, the more they repel each other, so they end up taking up exponentially larger space. The explanation about why we increase in size as we go to the left is a little bit more complicated. So lithium and neon are both in level 2, which means that they have 2 energy levels that surround the nucleus. But for some reason, neon, even though it has more electrons, has a smaller radius. So that kind of doesn't really make sense if you think about electron repulsion. That's what we just said. Like, wouldn't they spread out? But the other thing that is going on is we're increasing the number of protons. So when you have elements that are relatively similar in size, so they're on the same period on the periodic table, you have to consider the role that protons would play in drawing those electrons in. So lithium would have what we would consider a very weak nucleus with only 3 positively charged protons to attract negatively charged electrons, whereas sodium in comparison has a much stronger nucleus. So 10 positives is going to function in a really similar way to like increasing the mass of the sun. Like if our sun was twice as massive, Earth would be a lot closer to it because there would be stronger gravity. So this is called nuclear charge. The more you increase the nuclear charge, the closer you draw the electrons in. The ionic radius is the way the radius changes when the atom becomes charged. So you'll see from this picture, gray represents the original size, and for metals, we have the pink representing the change. Notice that all of the metals shrink in size. If you lose electrons, you decrease in size. It makes sense. If you look at blue in comparison, if you gain electrons like nonmetals do, then you increase in size. So oxygen -2 is always going to be bigger than regular oxygen because we're increasing the number of electron repulsion without changing the number of protons. Whereas lithium, +1, is always going to be smaller than lithium because we only have 2 electrons here, and in lithium regular we have 3 electrons, so there'd be more repulsion in that one. If you're comparing atoms to each other, you have to consider both factors. Are they charged? Are they neutral? What's going on? So we have to think, in this case, we have 1 uncharged atom, 2 charged atoms. What's the ratio of protons to neutrons here? So this one has 7 protons, but it has 10 electrons. This one has 10 protons, 10 electrons. This one has 12 protons and 10 electrons. So are we increasing our repulsion, decreasing our repulsion? What's happening? Largest radius. We're thinking which one would have the electrons spread the farthest out. That's going to be the one with the most electrons and the fewest amount of protons, which is going to be our nitrogen. The next would be this one because it has an equal amount, and then our smallest atom would be the magnesium because it lost electrons and decreased in repulsion instead of increased. Ionization energy is the energy required to remove an electron, which if that's written as a process, it would look like this. Neutral atom turning into charged atom by the removal of an electron. Okay, notice that the change in energy during this is always positive. So even though we sometimes describe elements as wanting to lose electrons, none of them really want to. There always has to be energy applied in order to take an electron away from an element, and that's because of the protons. All the electrons are attracted to the protons, but the distance from the protons and the number of electrons can affect the amount of endothermic energy that that's going to require. So for example, you'll see that ionization energy in general decreases down the periodic table. So it's much harder to take an electron from neon than it is from radon. Why? Because neon only has 2 energy levels, whereas radon has 6. Okay, 1, 2, 3, 4, 5, 6. So if you're trying to take an electron from the outside of neon's shell, it's going to be really close to those 10 protons, and that's going to make it pretty difficult to take. If you're trying to take an electron from the outside of radon's shell, it is really far away from the protons that are in the nucleus, which makes it less endothermic to remove. This concept is called shielding. Okay, the more shielded an electron is from the protons, the easier it is to remove. The other trend that you'll notice is we decrease in endothermic energy as we go to the left on the periodic table. So for example, it's much more difficult to take an electron away from neon than it is to try to take an electron away from lithium. Why? Okay, again, it goes back to how close are they to the protons and how many protons are there. Neon has a stronger nucleus. They both only have 2 energy levels. So if you have 10 protons, they're going to cling to that electron a lot harder than these 3 protons will. So even though they both still have an endothermic ionization energy, it's much less on lithium side than it is on neon side. The trend that you want to recognize from this chart is twofold. One, every single successive ionization energy is going to get harder. So once you've lost an electron, it's harder to lose the next one. If you've lost 2 electrons, it's even harder to lose the next one and the next one and the next one. And that's because you're increasing the hold that all of the protons have on the few remaining electrons that are left. The other thing that I want you to notice is not only is there a successive increase, there's an enormous increase once the valence energy level has been emptied. So for example, aluminum has 3 valence electrons. It's kind of hard to take the first one. It's pretty hard to take the next one. It's pretty hard to take the third one. It is insanely hard to take the fourth one. And that is because once we've gotten rid of the 3s2, 3p1, what's left behind is that 2p6 from neon. Okay, that's going to be virtually impossible to remove. The next fun thing that you'll notice is that it's not a perfect slope as we go from the right side of the periodic table to the left. Why are there some funky things going on? So boron, carbon, nitrogen, oxygen, fluorine, neon are in this order. You would expect there to be a smooth decrease in the difficulty of taking an electron away. But what we see is that for some reason right here, nitrogen peaks up just a little bit. Instead of being easier to take an electron from, it's actually harder to take an electron from. And that is because of this idea of stability. So full and half full orbitals are kind of stable. So we're talking about this 2p section having this perfect arrangement of 1 electron in each orbital, which gives it this semi-stable status. So trying to take this electron away is pretty easy for 2 reasons. One, this is not a full or semi-full stable orbital for the 2p section. 2, we have a little bit of electron repulsion going here, so that means it's going to want to go away. If we try to take this electron, we have a little bit of an uptick in difficulty because those orbitals are all half filled, which makes them semi-stable. Last but not least, we have kind of the opposite of ionization energy, which is electron affinity. That is the energy change associated with the gain of an electron, and notice that it is now a negative change in energy, which means that it tends to be an exothermic change. But it becomes less exothermic as we move to the left, and less exothermic as we move down. Why would it be less exothermic? So remember that this is essentially all about electrons being attracted to protons. If you have an electron being added to lithium's level, the protons are right here, that's going to cause kind of a happy situation where this electron and this proton are canceling each other out a little bit. Whereas rubidium, all its protons are way down here, so adding an electron to its electron cloud does make an exothermic change, but it's not as satisfying because the electron is so far away. And you'll see an increase in exothermic loss of energy as you move to the nonmetal side of the periodic table for two reasons. One, nonmetals have more protons than the left side of the periodic table. Two, we're creating an accomplishment here. Remember that half full and full is more stable. So by filling in that orbital right there, we've just stabilized this element. Now note, it is not a perfect situation. Okay, it's not a perfect transition in decreasing exothermic energy as we go to the left. So for example, beryllium here is a weird exception. Like, why does it not lose energy? Again, remember, half filled and filled means that they're stable. So when beryllium is being forced to add an electron to its electron cloud, it's basically being forced to gain an entire new block of orbitals. Okay, that's going to require energy. So instead of losing energy, beryllium would probably have to gain energy.